What is flaring? Flaring is the controlled burning of natural gas produced in association with oil in the course of routine oil and gas production operations. This burning occurs at the end of a flare stack or boom. Flare systems and their operation have been discussed by a number of authors of technical papers. Shore's paper, Making the Flare Safe, provides a general introduction to the systems used in the oil and gas industry. A complete flare system consists of the flare stack, or boom, and pipes, which collect the gases to be flared. The flare tip at the end of the stack or boom is designed to assist entrainment of air into the flare to improve burn efficiency. Seals installed in the stack prevent flashback of the flame, and a vessel at the base of the stack removes and conserves any liquids from the gas passing to the flare. Depending on the design, one or more flares may be required at a production location. A flare is normally visible and generates both noise and heat. During flaring, the burned gas generates mainly water vapor and carbon dioxide. Efficient combustion in the flame depends on achieving good mixing between the fuel gas and air and on the absence of liquids. Low-pressure pipe flares are not intended to handle liquids and do not perform efficiently when hydrocarbon liquids are released into the flare system. The percentage combustion efficiency of a well-designed and operated flare is in the high 90% range. Recent work by the U.S. Environmental Protection Agency has shown that combustion efficiencies are often greater than 98%. Gas being flared may come from a variety of sources. It may be excess to that which can be supplied commercially to customers. It may be unburned process gas from the processing facilities. It may be vapors collected from the tops of tanks as they are being filled. Sometimes the gas may be from process upsets, equipment changeover, or maintenance. Occasionally, a production shutdown may require the temporary flaring of all the gas stored on or arriving at a facility to release high pressure and avoid a catastrophic situation occurring. It is in the oil company's interest to realize as much value as possible from the hydrocarbon accumulations the company is producing. Therefore, it is also in the company's interest to minimize the amount of gas being flared. In this respect, the commercial aims of the company are consistent with good environmental practice. What is venting? Venting is the controlled release of gases into the atmosphere in the course of oil and gas production operations. These gases might be natural gas or other hydrocarbon vapors, water vapor, and other gases such as carbon dioxide separated in the processing of oil or natural gas. In venting, the natural gases associated with the oil production are released directly to the atmosphere and not burned. Safe venting is assured when the gas is released at high pressure and is lighter than air. Because of the strong mixing potential of high-pressure jets, the hydrocarbon gases discharged mix well with the air down to safe concentrations at which there is no risk of explosion. Venting is normally not a visible process. However, it can generate some noise, depending on the pressure and flow rate of the vented gases. In some cases, venting is the best option for disposal of the associated gas. For example, in some cases, a high concentration of inert gas is present in the associated gas. Without a sufficiently high hydrocarbon content, the gas will not burn and flaring is not a viable option. Sometimes the source of inert gas may come from the process systems. The purging of process systems with inert gas may in itself justify venting as the safest means of disposal. Safety aspects. The availability of a flare or a vent is absolutely necessary in oil and gas production operations. It ensures that safe disposal of the hydrocarbon gas inventory in the process installation is possible in emergency and shutdown situations. Where gas cannot be stored or used commercially, it is essential that the risk of fire and explosion be reduced by either flaring or venting. Even where associated gas is being sold or re-injected, small amounts of gas will still need to be flared or vented for safety reasons. Oil and gas processing and storage equipment is often operated at high pressures and temperatures. When abnormal conditions occur, the control and safety systems must release gas to the emergency flare or vent to prevent hazards to the employees or public. Good maintenance and operating strategies are the main mechanisms used to keep this already small volume as low as practicable. Emergency flares are normally fitted with pilot systems maintaining a small flame as the ignition source in case the full-size flare is activated. Recently, new flare equipment designed to operate without a pilot flame, and hence without emission when not active, was installed on a number of Statoil's production facilities in Norway. This equipment, built around high-reliability valves and ignition systems, is described in case study number 3. Another safety issue in the application of flaring and venting is the toxicity of the gases being disposed. In some situations, the toxicity of the gas relative to the toxicity of its combustion products may need to be considered when choosing between flaring and venting as a means of disposal. An example would be where gas containing hydrogen sulfide is being produced. Hydrogen sulfide is a gas that can be fatal if inhaled even at low concentrations. However, its combustion product, sulfur dioxide, is relatively less toxic. Environmental issues. People outside the oil and gas industry sometimes express concerns about the environmental impacts of flaring and venting. One such concern relates to the potential for global climate change. Both carbon dioxide and methane, the major component of natural gas, are known as greenhouse gases associated with concerns about global warming. Flaring produces predominantly carbon dioxide emissions, while venting produces predominantly methane emissions. The two gases have different effects, however. The global warming potential of a kilogram of methane is estimated to be 21 times that of a kilogram of carbon dioxide when the effects are considered over 100 years. When considered in this context, flaring will generally be preferred over venting the same amount of gas in the design of new facilities, where sufficient amounts of gas will be produced to run a flare. While there are still many uncertainties in our understanding of the complex issue of climate change, it makes sense to avoid the unnecessary release of carbon dioxide or methane into the atmosphere, where practicable. This points to a need to reduce emissions in a reasonably practicable way. The case studies in this booklet illustrate some of the ways the oil and gas industry is achieving those reductions. However, it is important to recognize that other environmental impacts also need to be managed. Conclusions. Flaring and venting are unavoidable processes in the production of oil and gas. Primarily for reasons of safety, some gas may need to be flared or vented at the production site. In other cases, for reasons that are often a combination of geography and availability of customers for gas, as well as local political factors, some or all of the associated gas produced with the oil is flared. Industry continues to seek opportunities to reduce the amount of gas being flared and vented. As an example, since the mid-1970s, the amount of carbon dioxide emitted due to flaring has nearly halved, and further reductions continue to be sought. New technologies are being developed to assist in the commercialization of associated gas reserves. Operation, maintenance, and design of flare systems are improving. New ways of storing associated gas are being investigated. While recognizing the need for these improvements, it is important to note that flaring and venting are relatively small contributors to anthropogenic greenhouse gas-related emissions. Overall, flaring and venting contribute only 1% to anthropogenic carbon dioxide emissions and 4% to anthropogenic methane emissions. The most important single conclusion to be drawn from the information presented in this booklet is the need for industry to be able to choose from among a variety of creative and common-sense approaches to address flaring and venting concerns in specific operations, whether with respect to selecting among technologies, choosing between flaring or venting, or maintaining a balance between climate change and other environmental concerns. Regulatory frameworks need to allow for best practicable choices to be made, rather than mandating a specific solution. No single approach will necessarily be appropriate for all projects or locations. The intrinsic value of the gas being flared or vented motivates the industry to manage the issue well. Government regulatory policy needs to be sufficiently flexible to facilitate the choice of the management approach most appropriate for the project and the situation. Appendices. Appendix A, Case Studies. Case Study 1, The Role of Market Forces, Flaring in the Nigerian Oil Industry. Case Study 2, Research and Development into Carbon Dioxide Storage, the Sleipner CO2 Project. Most of Nigeria's oil facilities were built in the 1960s and 1970s. In those days, gas was not a popular energy source. Gas was more difficult to produce and transport than crude oil. There were few market outlets. domestic and international, for gas, and there was little environmental awareness of the consequences of gas flaring. In the 1960s and 1970s, the main interest was in the development of the country's oil reserves. At this initial stage, the existing oil fields did not produce significant amounts of associated gas. This fact, coupled with the lack of a domestic gas market and commercial energy pricing policy, meant that installation of an expensive network of compression facilities and pipelines needed to link these scattered fields and market the gas could not be economically justified. Consequently, when the first small volumes of gas did start to flow to Nigerian industry, they were from non-associated gas reservoirs, which were a cheaper and more reliable source because they were produced at high pressure and did not depend on oil production. One of the earliest solutions to the dilemma of gas flaring in Nigeria was the reinjection of produced associated gas into underground reservoirs. SPDC, Shell Petroleum Development Company, was the first company in Nigeria to reinject gas, at Oguta in 1978. However, associated gas reinjection proved not to be a viable proposition in all cases. Most Nigerian oil reservoirs are technically unsuitable for large-scale reinjection. From the standpoint of export markets, Nigeria's physical isolation from the nearest major international gas markets in Europe ruled out a pipeline. This left the technologically more complex and expensive option of liquefying and shipping the gas. Nigeria's first liquefied natural gas (LNG) plant is currently being installed. There are already plans for future expansion. Case Study 1. The role of market forces, flaring, and the Nigerian oil industry. Most of Nigeria's oil facilities were built in the 1960s and 1970s. In those days, gas was not a popular energy source. Gas was more difficult to produce and transport than crude oil. There were few market outlets, domestic and international, for gas, and there was little environmental awareness of the consequences of gas flaring. In the 1960s and 1970s, the main interest was in the development of the country's oil reserves. At this initial stage, the existing oil fields did not produce significant amounts of associated gas. This fact, coupled with the lack of a domestic gas market and commercial energy pricing policy, meant that installation of an expensive network of compression facilities and pipelines needed to link these scattered fields and market the gas could not be economically justified. Consequently, when the first small volumes of gas did start to flow to Nigerian industry, they were from non-associated gas reservoirs, which were a cheaper and more reliable source because they were produced at high pressure and did not depend on oil production. One of the earliest solutions to the dilemma of gas flaring in Nigeria was the reinjection of produced associated gas into underground reservoirs. SPDC, Shell Petroleum Development Company, was the first company in Nigeria to reinject gas at Oguta in 1978. However, associated gas reinjection proved not to be a viable proposition in all cases. Most Nigerian oil reservoirs are technically unsuitable for large-scale reinjection. From the standpoint of export markets, Nigeria's physical isolation from the nearest major international gas markets in Europe ruled out a pipeline. This left the technologically more complex and expensive option of liquefying and shipping the gas. Nigeria's first liquefied natural gas (LNG) plant is currently being installed. There are already plans for future expansion. However, LNG is only part of the answer. Any successful program to end gas flaring in Nigeria depends on creating local markets. The key to achieving this lies with industry, which alone can harness the sort of volumes required. Although many industries are connected to gas pipelines, the major users of large volumes of gas so far are the National Electric Power Authority, NEPA, which uses gas to generate electricity, and the National Fertilizer Company, NAFCON. Several new projects that will use associated gas are being planned, but there remains a need for more gas-based industrial development. For that to happen, consumers need incentives to use gas rather than other energy sources, and suppliers need incentives to build expensive gas gathering, compression, and treatment systems. Harnessing the gas which is currently being flared must, at the end of the day, be an economic proposition. The price has to be right to justify the use of gas by the consumer. the price must also justify the supplier's investment in the necessary plant and equipment. To achieve this, allowances have to be made in fiscal and gas pricing policies and in operating agreements. The oil industry in Nigeria is working with the government to accomplish these objectives. Case Study 2. Research and Development into Carbon Dioxide Storage, the Sleipner CO2 Project. A unique event took place in October 1996 when Statoil, Norway's state oil and gas company, began storing carbon dioxide under the North Sea. Statoil's Sleipner gas field is situated 250 kilometers west of the Norwegian coast. As with many gas fields around the world, extracting the gas also yields unwanted products. In this case, the gas contains 9% carbon dioxide. For the gas to be marketable, this concentration must be reduced to 2.5%. Historically, gas contaminants have been typically vented to the atmosphere prior to selling the natural gas. However, Norwegian government concerns about carbon dioxide emissions from human activity and their potential contribution to global warming prompted a decision to impose a carbon tax on oil and gas production. State Oil and its partners started to look at radically new technology in order to commercialize the Sleipner gas reserve. They eventually decided that it might be technically and economically feasible, considering the carbon tax, to separate the carbon dioxide from the hydrocarbon gas and re-inject it into deep underground formations. A new offshore platform, Sleipner T, containing all the necessary equipment, was sited alongside the existing production platform, Sleipner A, in 1996. On Sleipner T, the carbon dioxide contained within the natural gas is separated by a complex chemical process. The extracted carbon dioxide is then compressed and injected into a water-filled sandstone reservoir 1,000 meters below the seabed. Using this system, over 1 million tons per year of carbon dioxide is being pumped below the ocean floor instead of the atmosphere. This technology is still in its infancy, and much will be learned from its use on Sleipner. The owners of the field have agreed that an international program is to be formed in order to monitor and research the performance of this facility so that the underground storage of carbon dioxide can be more fully understood. The International Energy Agency's Greenhouse Gas Research and Development Program is working with Statoil to establish and manage this program. The major task for this group will be to monitor the stability of the underground reservoir and to observe the development of the expanding carbon dioxide bubble in order to ensure that the gas remains within the reservoir. Case Study 3. Technical Innovations in Flare Design, the Gullfax Project. Technological innovations pioneered in Norway could, in some situations, provide a means of eliminating the small amount of pilot gas which is currently needed on conventional flare systems. The technique, which has been pioneered on the North Sea Gullfax field, involves routing gas, which was previously flared back to an existing gas export system, through pipework with a valve which can quickly divert the flow to the flare stack if the pressure starts to increase. As an added safety measure, the piping contains an extra loop with a rupture disc to provide a second fail-safe escape route if the valve does not open. An automatic ignition system, comprising a gun fitted at the top of the flare stack to shower specially formulated pellets at a steel plate, provides sparks to light the flare when it is needed. Under normal conditions, the piping in the flare stack is protected against a buildup of explosive mixtures by being filled with an inert gas from a nitrogen generation plant. A critical factor in developing the system was being able to convince the Norwegian safety regulator that the system would meet their requirements. The breakthrough was achieved when it was decided to add the loop with the rupture disc. This ensured that there would be two possible routes by which gas could reach the flare stack in an emergency. After a number of startup problems, the Gullfax C platform flare has now been extinguished while flaring on Gullfax A is down by 60% and will end in the near future. If the experience proves positive, steps to reduce flaring on some other platforms are likely. However, the technique is only suitable for use with inclining flare stacks rather than the vertical stacks, fitted on many of the existing oil developments around the world. After Case Study 4, local factors influence flare design in Venezuela. PDVSA, the Venezuelan national oil company, uses a high-pressure gas injection system to improve oil recovery in its operations in the eastern part of the country. The high-pressure gas injection system employs the largest high-pressure gas compressors for well injection in the world. One of the necessary components of this system is equipment which will safely flare the compressed gas in the event of either planned or unplanned shutdowns. In the case of this gas injection project, several local environmental constraints presented a unique set of problems for system designers. Due to the very high-profile nature of the project and the plant's location near a major industrial residential city, a 100% smokeless flare operation was required. A relatively small plot was available on which to site the flare system. The compression plant is situated near a major highway and is surrounded by existing production and oil processing plant facilities. Due to the proximity of a nearby international airport and other local safety considerations, there was a need to restrict such factors as flare stack height and heat radiation intensity. The system needed to be capable of handling a wide range of gas flow rates. An unreliable local power supply produced the requirement that all flare system controls be fail-safe with a 24-hour automatic battery backup. One of the key design considerations was the need for smokeless operation within the limitations imposed by stack height and radiation. A flare design had to be selected which would not only provide optimal mixing of gas and air to produce virtually smokeless operation over the entire flow rate range, but would also produce a small but very intense flame with low radiation effects. To handle the full flow range, a 3-stack array was installed that included 2 high-pressure and 1 low-pressure flare tip. Before installation, the flares were tested individually and collectively and performed smokelessly within the radiation limits over the full specified range of operation. Pre-installation checks also included a check of the battery backup system and the instant relight system that immediately ignites the flare or shuts in the gas flow if the flare goes out for any reason.